Figure shows a coil PQRS having n turns rotating in a uniform magnetic field vector B with a uniform angular velocity omega about the x-axis. The magnetic field vector B is directed along the y-axis. Let the direction of area vector A of the coil perpendicular to the plane of the coil make an angle theta is equal to 0 with the direction of vector B at time t is equal to 0. The flux phi linked with the coil at that time is phi 0 is equal to n vector A vector B. That is equal to NAB cos 0. That is equal to NAB. The coil is rotating with an angular velocity omega. Let it come to a position such that at time t, the area vector A makes an angle theta with the vector B. Clearly, theta is equal to omega t. Therefore, the flux linked with the coil at time t will then be phi t is equal to NAB cos omega t. As the coil is continuously rotating, the flux linked with it goes on changing with time t according to the equation. Applying Faraday's law, we can write the EMF induced in the coil at time t as V is equal to minus d phi t upon dt. That is equal to NAB omega sin omega t, where NAB omega is equal to Vm, the maximum value of V. Therefore, V is equal to Vm sin omega t. Equation shows that the EMF induced in the coil varies with time as sin omega t. Figure shows slip rings A1 and A2 connected with the two ends of the coil, making sliding contacts with brushes B1 and B2, and the induced EMF can be carried to the brushes by this arrangement. When the coil is at its position theta is equal to 0 at t is equal to 0, the voltage difference between B1 and B2 is 0. It then increases with time t till t is equal to pi upon 2 omega. Thus, starting from 0 at t is equal to 0, it increases to Vm at time pi upon 2 omega. During this time, B2 acts like positive terminal and B1 acts like a negative terminal, and then decreases from t is equal to pi upon 2 omega to t is equal to pi upon omega, when it again becomes 0. During the further rotation of the coil from time t is equal to pi upon omega to the time 3 pi upon 2 omega, V takes a negative value, so that now B1 acts as a positive terminal with respect to B2. Its potential becomes maximum at t is equal to 3 pi upon 2 omega and again decreases to 0 at t is equal to 2 pi upon omega. This way the cycle goes on repeating, that is, with a time interval of pi upon omega, the terminals B1 and B2 alternately go on changing the polarity with respect to each other. Such a voltage is called an alternating voltage or AC voltage, and the device which generates such a voltage is called an AC dynamo or an AC generator. Figure shows a circuit in which this source of AC voltage is connected with a resistance to complete the circuit. At time t is equal to 0, the voltage difference between A and B is 0. So, no current flows through the resistance R. Now, as the voltage increases with time from t is equal to 0 to t is equal to pi upon 2 omega, a current I is equal to Vm sin omega t upon R flows along the direction A, C, D, R, E, F, B, with its magnitude changing with time as given by the above expression, with the terminal A becoming positive with respect to B. After attaining its maximum value at t is equal to pi upon 2 omega, it decreases to 0 at t is equal to pi upon omega, and then reverses the direction as the current flows in the direction B dash, F dash, E dash, R dash, D dash, C dash, A dash, and the terminal B now becomes positive with respect to A. The cycle thus repeats with a time interval of 2 pi upon omega. Such a current flowing through R is shown as a broken line and is called alternating current or an AC current.